Welcome to an Achieving Science video. This video is going to cover electronic structure. Let's begin by having a closer look at an atom. So if we take an example of sodium, if we find sodium in the periodic table, we can see it's given the symbol Na. Along with that symbol there are two numbers, the number 11 and the number 23. But what do these numbers mean? Well, first of all, an atom is made up of three subatomic particles. It's made up of protons, neutrons, and electrons. But how many of these particles does sodium actually have? Well, we can determine this by these two numbers. First of all, if we use the bottom number, the 11, this is the atomic number. It is also referred to as the proton number, as this is the number of protons sodium has, in this case 11. The 23 on the other hand is the mass number. This is made up of the total number of protons and neutrons. So therefore, if we know that there are 11 protons, there has to be 12 neutrons in order to equal a mass of 23. So the next question is then, if we know the number of protons, we know the number of neutrons, how many electrons are there? Well, in an atom, there is the same number of protons and electrons. This makes the atom neutral. So let's have a look at the sodium atom then in a bit more detail. The sodium atom then has a nucleus at its centre. This contains the protons and the neutrons. Around this then, there are the electrons. The electrons are found within energy levels, or shells as they are referred to. In the first shell, there is a maximum of 2 electrons. Because sodium has 11, this is full. The electrons then move to the second shell that is capable of holding 8. This is full. This makes 10 so far, and therefore it needs a third shell to contain 1 electron to equal 11 electrons. These electrons are negatively charged and held in place due to the attraction between the nucleus and the electrons. Electrons will always fill the innermost shells first, remembering that the innermost shell holds 2 and the next shell can hold 8. So as we say, what actually holds the electrons in place? Well, the protons have a positive charge. Neutrons have no charge. And as the nucleus is made up of protons and neutrons, this is why the nucleus is referred to as being positively charged. On the other hand, electrons have a negative charge, and therefore the positive nucleus attracts the negative electrons, and this is called electrostatic attraction. Then we can move on to, well, why do the electrons not actually appear in the mass number? Well, protons and neutrons have a relative atomic mass of 1. Electrons, though, have a negligible mass. This means they virtually weigh nothing. If we look at another atom then, what can we see? If we choose another element, let's choose the element aluminium, given the symbol Al, atomic number of 13 and mass number of 27. Aluminium therefore has 13 protons, and because its mass number is 27, if we subtract 13 from it, we can calculate it that it has 14 neutrons. As it has 13 protons positively charged, it must have 13 electrons. We can then draw the atomic structure of aluminium. 2 electrons in the first shell, 8 in the second shell, and then 3 in the third shell. If we total those all up, 2 plus 8 plus 3, there are 13 electrons. We have drawn it correctly. Now remember that the electrons will always fill the innermost shells first, so that's another way we can tell that we've drawn it correctly. But there are other ways you can check the electronic structure, and this is by looking at the periodic table. The periodic table is provided to you in your examination. It is a great tool in chemistry. The periodic table then is made up of groups. So we have group 1, 2, 3, 4, 5, 6, 7, and sometimes referred to as 8, or most commonly known as group 0 on the end. The group number indicates the number of electrons in the outermost shell of the atom. And therefore, if we find aluminium, aluminium can be located in group 3. So this means that it has 3 outer electrons. We have drawn it with 3 outer electrons, and therefore we have drawn it correctly.